It's 3:25, so I will take up question 3. Here we are having two events A and B such that the probability is between 0 and 1, not inclusively. We want to verify that the two condition is equivalent to the independence of A and B. Independence of A and B means that probability of the intersection is equal to probability of A times probability of B, like this. So we want to show that each of the statement here is equivalent to this statement. First one, I have probability of A given B plus probability of A complement is equal to 1. Then if I expand out this term, I would have probability of the intersection divided by probability of B. And you should realize that I don't want to have the term probability of A complement, because what I want to reach just involve probability of A intersect B and then probability of A or probability of B. It does not have anything to do with probability of A prime. So I will not keep this term. I have to rewrite it in terms of one of these three expressions. And the easiest way is converting probability of A prime to probability of A by this equation. We have probability of A complement is equal to 1 minus probability of A. And then you would have probability of A intersect with B divided by probability of B is equal to 1. I will bring the whole expression here to the right-hand side. So I have minus 1 and then plus probability of A. And you see that the 2, 1 cancel out. So I'm left with probability of A. And if I cross multiply, I will get this expression. And it means that A and B are independent. So we show that the first condition is equivalent to independence of A and B. That is the first one. Let me know if you have any question. The second one, probability of A complement given B is equal to probability of A complement given B complement. Intuitively, this should make sense to you. Why they are equal to each other? Because it's saying that knowing B happen, the chance that A complement happen is the same as when you know B does not happen, which means knowing B happens or not does not change the chance for A complement to occur. So it just means it doesn't change the probability for A to occur as well. So it means that A and B are independent. So that's how you explain it intuitively. But mathematically, you still want to bring it to this expression. What you can do is using conditional probability on each side. Here, I have probability of A complement intersect with B is the same as probability of B minus probability of A intersect with B. I hope you see why. Because let's say you have two events A and B. Then A complement intersecting B is this part. And you calculate that part by taking the whole circle, which is B. Subtract the intersection, which is probability of A intersect with B. So that's why this numerator can be rewritten as this one. And you see here, A complement intersect with B complement by the Morgan theorem. It is a, actually, let's not use that. You can use the same logic and write probability of B prime minus probability of A intersect with B prime. You can use this, it is fine. Divided by probability of B prime. And here you can simplify the fraction. This fraction become probability of B divided by probability of B, which is 1, minus probability of A intersect B over probability of B. And we do the same thing for the right-hand side. Probability of A complement divided by probability of A complement is 1. And we are left with this one. I will erase this Venn diagram. Okay. And from this step, you can see that two sides are equal and they both have 1 minus something, which tells us that probability of A intersects B divided by probability of B is equal to probability of A intersect B prime divided by probability of B prime. And you can see that, okay, the left-hand side, it consists of the terms that you want, which is the intersection and probability of B. That's what you want. However, the right-hand side, right now, it is having the terms that you don't want. For example, like probability of B complement. That is not something that we want. Or probability of A intersect with B complement. We also don't want that term. So I just keep the left-hand side to be the same. And instead of A intersect with B prime, I can write it as probability of A minus probability of A intersect with B, so that it involves the term that I want. And then divided by 1 minus probability of B, because it is probability of B complement. And now you can cross multiply both sides. You will multiply this numerator with this denominator. So you have probability of A intersect B minus probability of B times probability of the intersection is equal to this denominator multiplied with this numerator. And you can see that two terms minus probability of B multiplied with the intersection is canceling each other out. Which just leave you with probability of the intersection is equal to probability of A times probability of B. Therefore, they are equal to each other. So A and B are independent. Is there any other question? Let me know if you feel lost at any step. If there's no question, I will let you work on question 4. You should think about like if A and B are independent, then what is the relationship between A complement and B complement? if we look at the definition for independency, like knowing some information about A does not reveal any information about B, then it also means that knowing some information about A does not increase or decrease the chance that B happen. Therefore, it also does not increase or decrease the chance that B complement happen. Therefore, A and B complement are also independent. And it also means that if you know some information about B complement, then it does not increase or decrease the chance that A happen. Therefore, it does not increase or decrease the chance that A complement happen as well. Therefore, A complement and B complement are also independent. So from A and B are independent, we know that A complement and B complement are also independent. Therefore, probability of A complement intersect with B complement is just probability of A complement times probability of B complement. We know probability of A is 0.7. Therefore, probability of A complement is 1 minus 0.7, which is 0.3. So I'm having 0.18 equal to 0.3 times probability of B complement. Therefore, probability of B complement is 0.6. So part 1, probability of A, B complement, since they are independent, we can have probability of A times probability of B complement, which is 0.7 times 0.6. It is equal to 0.42. So that is the first part. The second part is probability of A complement and B. Again, since they are independent, I can just multiply their probability. Probability of A is 0.7. So probability of A complement is 0.3. Probability of B complement is 0.6. So probability of B is 0.4. So the product is 0.12. The last part, we can see that we want to calculate probability of A union B. And we are having probability of A complement intersect with B complement. And by De Morgan law, you have it is A union B and complement. And it is just 1 minus probability of A union B. So you have probability of the intersection is 1 minus probability of the union. And the intersection is happen to be 0.18. Which means probability of A union with B is 1 minus 0.18, which is 0.82. Any question about this part? Can you go over the third one again? Yes. I started with probability of A complement intersect with B complement. And then this set by De Morgan law, it is A union B complement. From here to here is just De Morgan law. And then probability of something complement is equal to 1 minus probability of that something, which is A union B. And this is the quantity we are trying to calculate. Yep. If we are good, we can attempt question 2. Will you explain the sentence for each I? Yes, it just means the probability that the box have 0 bulbs, like 0 defective bulbs, is 1/5. And probability that a box have 1 defective bulbs is 1/5. Similarly for 2, 3, and 4. But a box will not have more than 4 defective items. Does that make sense? Yeah. So what we are having here is, let's say it is our simple space. And is partitioned based on the number of defective bulbs inside each box. So let's say this is where, oops, my pen's really not working today. Let's say this is where you have 0 defective. Is the first one 4/5 to the power of 1/10? How do you get that? You should probably use some conditional probability here. And this part belong to when a box have 1 defective box, and these 2, 3, and 4. So a box cannot have more than 4 defective items, at most 4, and at least 0. And let's say you are having some event like this. The event in the green part, it represents for the event that you sample 10 items from a box and none of it is defective. So that's what the green part is representing. For the first one, we know that we choose 10 bulbs and none of them is defective. And we want to calculate the probability that a box contains no defective, which means probability of 0 defective, given that you choose 10 and none is defective. This is a quantity that you are trying to calculate. If you use Bayes' theorem, it will give you the numerator is probability that a box contains 0 defective, multiply with probability that you choose 10 box and non-defective, given that the box itself have 0 defective item. And we will want to divide it by probability that you take 10 items and none of them is defective. So this by Bayes formula. Or you can just write conditional formula and then work up from there. The numerator is pretty easy to deal with. Probability that a box have 0 defective item is given. It is 1/5. The question said here, probability that a box has 0 defective box is 1/5. And similarly for 1 up to 4. And now I'm interested in the probability that given my box does not have any defective item, then what is the chance that I sample 10 items and none of them is defective? This probability has to be equal to 1 by common sense. Because if inside the box there is no defective, then there is no way that you can take something defective out of it. So for sure that the 10 items that you take from the box, none of them will be defective. That's why this probability is 1. And now calculating the denominator, it is pretty long. You will have to think about it. Probability that you take 10 items and none of it is defective. It means that you want to calculate the whole circle here. But in order to do that, you will have to calculate this area. And then you add with this area. and then you add with this, and add with this, and add with this, which means you have to calculate 5 distinct regions and then adding their probability together. So the first region is when you take 10 items and none of them is defective, and the box have 0 defective. Then again, using the multiplicative law, it is just probability that the box have 0 defective item. Multiply with, you'll get 10 items. None of them is defective, given that the box have 0 defective. The first probability is 1/5, it is given. The second probability is 1 for the same reason I just explained. We would do the same thing to calculate 10 and none of them is defective, and the box have 1 defective item. Then it is equal to probability that the box have 1 defective item, and then probability that you get 10 non-defective, given that the box have 1 defective item. The first probability is just 1/5, it is given. The second probability, if you think about it, your box has 120 in total. Out of that, 1 is defective and 129 is non-defective. So what is the chance for you to pick out 10 boxes and none of them is defective? Which means out of 119 non-defective, you pick out 10. And then divided by the total number of ways that you can pick 10 boxes out of the box without any restriction, which is 120, choose 10. If you apply the same logic to get probability that you get 10 items, none of them is defective, and the box have 2 defective items, then you would get 1/5 for probability of having 2 defective in the box. Multiply with, given that the box have 2 defective, which means it has 128 non-defective. What is the chance that you get all 10 non-defective? Then it is choosing 10 from 118 non-defective divided by choosing 10 without any restriction. We are running out of time, so what you have to do next is calculate the same thing for the case when it is 3 defective and 4 defective, and then adding all these probability together. Then you will get the denominator, and then you take the numerator divided by the denominator. You will get the answer that you want. Any question about this part? It is a long question and it requires lots of computation. If there is no question, then it is the end of our tutorial. You can try to continue solving the rest by yourself, and if you feel stuck, feel free to post on Piazza. Otherwise, have a good night, everyone.